Hey everybody, welcome back to the channel. Today we're going to be talking about types of forces that exist. We've brought up this idea of force a few times now. We've looked at what's going on with Newton a bit, and he's got some laws related to how things move. And now we're going to try to figure out what sort of forces are there that exist within the universe. And we could start out, and we're going to talk about the big ones that exist. Then we're going to get down more into what is more practical. And the big ones that exist are all dealing with action at a distance. Okay? There's four forces of nature that exist. And they're ultimately the fundamental forces that allow the planets to spin and the stars to burn and everything works. Okay? The universe works because four forces of nature exist and they keep it all together. And all these forces act at a distance, which is really kind of key to their behavior. Gravity, of course, is probably one of the big ones. Without gravity, we wouldn't have planets and stars. The Earth wouldn't revolve around the sun. The moon wouldn't revolve around the Earth. Things wouldn't quite work right if gravity wasn't here. Ultimately, it's dependent upon the amount of mass that's in the object and the positions of two objects. That's what really matters. So the distance between things and how much mass they have when you're looking at gravity are the important factors. Electromagnetism is another force. We're actually going to explore this a bit in class. We're going to play around with some electromagnets at some point. Ultimately, electricity and magnetism might seem a little bit different, but they were found to actually be very closely related. And there's a whole series of equations called Maxwell's equations, which relate electricity and magnetism together. And it kind of sparked this whole idea that we could link all the primal forces, all the four forces of nature, could be linked together through some sort of grand unification theory, which is one of the holy grails of science. The other two forces are called the strong force and the weak force. Strong force ultimately is what holds the protons together inside the atomic nucleus. It's one of the most powerful forces in nature. It literally binds the quarks together to form the protons and the neutrons. So that force, which goes on the nucleus of all the atoms, is actually the most powerful one that we can find. The weak force, on the other hand, is actually kind of being able to see in stars. It's what is responsible for nuclear fusion and allows these sorts of things to go on. You might have heard the word boson before, and that's really what's happening with the weak force. And it's why we have stars, is what you should probably know about it at this point. So those forces are pretty big concept ones, and we're not going to really worry too much about the big picture right now. We want to get more down into the nitty-gritty of, a cat pushing your cell phone off the table. That is a little bit more the level of physics that we're at. So ultimately, when we're looking at F equals ma, we're looking at an applied force or a contact force, and it's creating an acceleration in an object with mass of m. So we've done a bunch of problems about force equals mass times acceleration at this point. F equals ma a little bit. But now we want to try to get a little bit deeper into it. Try to analyze situations and understand what's going on with the forces. Beyond the craziness of the kitty wanting to push the cell phone off the table, my cat likes to clean off the walls, likes to clean off the tables. She's really into knocking things down. So ultimately, we call any applied force F, and then we put applied down at the bottom, APP, in lowercase, a little bit of a subscript there. Any sort of push or pull is an applied force. Ultimately, if you apply enough force, the object will start moving once you've overcome its inertia. The normal force is a force that ends up working with gravity a little bit. So gravity is always pulling us down, right? Ultimately, when we're pulled down, like this woman would be onto the rock there, the rock is pushing back up. Okay? So the woman's being pulled down, the rock is pushing her up. And those forces have to be balanced. So the force of gravity can't be pulling her down into the earth, or else she'd fall into it. And the force of the rock can't be like shoving her up into the air, because she doesn't like spring up into the air, she doesn't fly away. So ultimately we know that the force of gravity and the normal force are balancing each other. And so we have the normal force in pretty much all the pictures, or all the force analysis pictures we're going to talk about tomorrow. Whenever there's gravity to balance it out, as long as you're on the ground. If you're falling, you don't usually have a normal force. You would have another type of force that we'll get to in a second. Friction is a very common force. Friction is going to oppose your motion. And friction comes in a couple of flavors. You can either have static or you can have sliding friction. So the ladies here riding their bicycles are experiencing a sliding friction. That friction is opposing the force of the bicycle moving forward that they're giving with their legs. The surface that you're riding on is going to provide different frictions. So here, riding in wet sand is going to provide a different friction than if the sand were dry, or if I was on asphalt or concrete or any sort of different material. Air resistance would be the force that would oppose us were we to be, or at least oppose gravity, if we were falling through the air. So instead of the normal force, it would be air resistance. And of course, you can increase your air resistance by getting more area to capture that air. That's kind of the principle of a parachute, is that by adding enough air volume, we can capture enough of it to slow down motion if you're free falling. Tension, like a puppy would put on its toy, is another force that goes on with any strings or ropes, all these sorts of things. And ultimately, it's a property of the material to see how much tension can be had. Like if you look at fishing wire, a lot of fishing string ultimately will tell you how big of a fish, how much weight, force it can handle. When you're trying to catch different fish, you don't want to use something that is too light for the fish that you're going after. If you are using too light of a rope, it will fray and break when you put too much force on it. So the tension in a rope hopefully is opposing, or is enough to hold the object that it is holding up. Springs, of course, also have their own force. Each spring is kind of unique. Springs and rubber bands work very similar. That there's little imperfections and various ways that you make them, different materials you make them from, that will provide a different experience for the springs. So ultimately, spring forces are extremely common in physics. Now, one thing that can happen is that you can get a little bit confused between mass and weight when we're dealing with forces. Weight is a force. Weight is the force that comes from gravity pulling on your mass. Okay? Mass is how much stuff I have. We've been talking about mass since we got into our definition of matter in the very beginning. So matter was anything that had mass and took up volume and space. Well, mass is the stuff that things are made out of. It doesn't matter if I'm on the moon or on Earth or on, Titan. None of it matters as far as how much mass I have. However, the weight of that mass changes dramatically. So the weight I have on the moon is about a fifth the weight I would have on Earth. Because the gravity on the moon is about 1.6 meters per second squared for its acceleration. While on the Earth, it's 9.8 meters per second squared. Another thing to understand is sliding versus the static friction. Okay, so when I am experiencing sliding friction, I'm sliding across a surface. And ultimately, there's going to be some sort of coefficient of static friction. It's just a number I multiply the normal force by. And that number changes depending upon what material I'm on. Like I mentioned earlier, that wet sand would have a very different amount of friction than, say, asphalt. And that's reflected in their coefficient of static friction, or of sliding friction in this case. Usually, sliding friction is a lot less than static friction. If you've ever tried to get an object moving, like imagine trying to move some furniture. Once the furniture is going, it's a lot easier to keep it going. While it's stopped and you're trying to get it going, there's a lot to overcome. And that is the static friction. Static friction is the friction we experience when an object is at rest, like relative to another object, and you have to start it moving. And generally speaking, you can push on an object, like try pushing on a refrigerator at some point, it probably won't necessarily move. So the static friction has a cap, basically. That cap would be the coefficient of static friction times the normal force. Once you exceed that cap, then the object starts moving. And it usually takes less force to keep it rolling than it does to get it going. Okay? So be aware that static friction generally is greater than sliding friction. Well, that's really about it as far as the types of forces. You're going to want to learn these. You're going to need them for what comes next, which is free body diagrams, which allow us to kind of graph out a situation that's going on in physics and figure out what the forces are so that we can figure out usually an F equals ma calculation or some other sort of physics calculation by reducing all the forces down and seeing what all is going on. And if you don't know certain types of forces, like that there's air resistance if I'm falling, then it is really hard to draw those. So make sure you learn these terms and learn what they mean and have them at the ready, and you'll do just fine with what comes next. That's about it, guys. Have a great night, and I'll see you in class tomorrow.